The main motivation for our work here at UCL is to try and observe quantum effects in macroscopic objects, even objects that are large enough to see with the eye. The particular system we use are optically levitated glass spheres, which act as harmonic oscillators in the field of an optical cavity.
We can then start to cool that oscillator by sending laser light detuned from the cavity mode. The laser photons gain a single vibrational quantum of energy from the energy of the oscillator before being emitted from the cavity. And this causes cooling of the oscillator. We also see the reverse process where the photon loses some energy to the oscillator before being emitted. And if we have a red detuned laser, then we get more of the former process than the latter, and hence cooling.
This isn't a new system which we're studying. Chang previously proposed that you could have two optical fields inside your cavity, one which localizes the trapped sphere and the other which cools it down. And previous work by our group showed that if you let both fields take on each of these roles, then you can get enhanced cooling. So this would be two optical fields with a 90-degree phase shift, but of similar strength and detuning from the cavity mode.
This paper looks at the same system but examines the relationship between the size of the sphere and the coupling between the light field and mechanical motion, so to see more effective cooling. If the bead gets too large, then it no longer behaves as a dipole. Scattering heating consequently becomes more significant, and not enough of the bead is trapped in or near to the point of maximum field intensity.
We have found and experimentally verified that spheres with a diameter of about 200 nanometers, which is 20% the wavelength of the trapping light, will give the best cooling outcomes. Exploiting the size of the sphere to increase the cooling is more desirable than just increasing the power of the cooling laser, because that leads to additional scattering, and that heats the sphere.
So here we see a Fourier transform of the position squared operator. The lower frequency peak is associated with the gain of a mechanical phonon, the energy being supplied by a photon shifted from the central mode frequency to a lower frequency. The higher frequency peak shows the propensity of the reverse process. As we approach the ground state, it becomes harder to remove energy, to the point where at the ground state itself there is no lower energy destination at all. As a result, the higher frequency peak is increasingly suppressed as we approach the ground state. This asymmetry is purely a quantum phenomenon.
This paper has shown that it is experimentally feasible to cool glass spheres in an optical cavity to a centre of mass motion of less than 1 phonon on average, which would be a quantum ground state.